Okay, good morning, everyone. One announcement first. I will not have my office hours at the usual time. I have like meetings and workshops and seminars and events like packed through. So I'm teaching from 9 to 12, and then right from 12 o'clock onwards until 4 o'clock, I'm just like, my schedule is just packed. Anyway, so I will be in my office between 4 and 5. So if you wish to stop by in person, I will be available between 4 and 5 today. Before that, if you have any questions, send me an email. I will be able to answer email. So again, between 12 and 4, if you wish to have an answer about something, send me an email. And then if you wish to see me in person, then between 4 and 5, and then after 6 o'clock on Zoom. Okay. The reason I'm mentioning is because we will cover node voltage analysis today. I will go over the theory and then solve an example problem. And then there's homework that is due on Sunday night. And then Monday's quiz will be based on node voltage analysis. And so there's about 3 days, well, just slightly short of 3 days for students to study and prepare for node voltage analysis. Okay, so I will take this slow. I will go over the entire example, go over each and every single concept. The homework is not long. There's only 3 problems on it, plus 3 extra credit tutorials. So again, there's only 3 problems, and my plan was to cover it in class itself, the homework problems, but we just didn't have enough time in the previous class. So what I'm going to do is I will make either a short video or I will create a short slide and I will post it in the class notebook so students can access it directly. So homework hints and help to solve those 3 problems. Okay. All right. So let's get started on node voltage analysis. Well, not started. We started last class. Let's continue with node voltage analysis. So we have, when we apply a source, connect a source to a circuit, we have unknown voltages and currents that appear in a circuit. We wish to solve these unknown quantities mathematically. So we need equations. We need to generate equations from the circuit that we have. To generate these equations, we apply a variety of techniques. For node voltage analysis, we apply KCL, current law, Kirchhoff's current law, to generate equations for node voltage analysis. Okay. So what is node voltage analysis? Well, we take all the nodes in a circuit, we assign labels to every node, and we assign node voltages to every nodes. And then we apply KCL to express each resistor voltage in terms of the node voltages. And so the way we do that, I will explain by looking at these 2 examples. So in this example 1 above, we have a single resistor with a value of R. R is connected between A and B. Those are the 2 nodes, right? It's a 2-terminal element, so it has 2 nodes, 2 connections, A and B. The label can be anything. You can label it X, Y, Z, 1, 2, 3, doesn't really matter. Okay. In this case, we just keep things simple. We choose A and B. And then once we choose A and B, have my node voltages VA and VB. Okay. In this case, of course, it's already given to us. Then once we mark the nodes and the node voltages, we assume a direction for the current I. We assume a direction and we provide a label for the current that is flowing through that resistor. In this case, again, it is already given to us. I is going from left to right. Current for a passive component flows from high to low or low to high? High to low, plus to minus. So conversely, the point of entry is plus or minus. And so I'm saying VA is higher than VB. So the polarity of that voltage simply indicates which end of that resistor has a higher potential, has a higher electric potential compared to the other end. So VA is higher than VB because current I is going from left to right. In this example, it is given to us. When you solve a problem, nothing will be given. You have to make the assumptions. Remember chapter 1, I stated, we make assumptions at the beginning of analysis. The assumptions are based on certain rules. They are based on certain logic. It does not matter what assumption you make. It could be the opposite. Your answer will still be correct. Okay, and we'll see that in the example problem. So if I was to write an expression for the resistor voltage VR from Ohm's law, I can write VR is I times the resistor R. So the current I is simply VR over R. Okay. Setup of the problem. Nodes A, B, voltages VA, VB, current I, make an assumption of the direction, then leads to conclusion about the polarity, which is plus and minus. We apply Ohm's law. I can express the current I in terms of the resistor voltage and the resistor. So I equals VR over R. Now, here's the important part. Node voltages will allow us to describe VR in terms of the node voltages. So since we know VA is plus and VB is minus, how can we express or write out VR? Voltage between any 2 points is the difference in electric potential between those 2 points. Difference means minus, yes. Okay. So it'd be VA minus VB divided by R. And now we have expressed the current in terms of the node voltages. At this point in the solution, we will plug in all the known values. Known values means given to us. The resistor values will be given to us. If we have a current source, as we will see in the example, that current source value will be given to us. If you have a voltage source, that value would be known to us. So we would simply plug into those equations. We will reduce it and rearrange the terms in the form of a linear equation. AX plus or minus BY plus or minus CZ equals D, where A, B, and C, or sorry, X, Y, and Z are my unknown variables. Those unknown variables would be the node voltages because we are solving for the node voltages. Make sense? So you would get an expression like, A times VA minus B times VB is equal to some constant C. Any questions? So far, so good. Let's take 10 seconds. Let me know if you have any questions. No? All right, then let's look at the second example. 3 resistors this time connected at node B in the center. And then we have the outer 3 nodes, A, C, and D. So we label the node voltages VA, VB, VC, VD. Current directions are also given to us, I1, I2, and I3 flowing through those 3 resistances. Okay. Based on, oh, almost fell over. Based on the current directions, we can state the relationship of each node with respect to the other node. So if you take a look at I1, what can we say about VA and VB? Which end is higher? So we mark VA with a plus, and this end would be minus. And that is VR1. How about R2? Which end is higher, B or C? B, because current's going from B to C. And then how about I3? B higher or D higher? I heard D or B? B. Minus. Let's call this VR3. We'll call this VR2. Sometimes students do have the question of how come B is minus, plus, and plus. And the answer would be that is not, the plus and minus signs solely belong to that resistor itself. It does not belong to the node. Okay, the plus and minus is the polarity of the voltage of that resistor. It simply indicates which end of the resistor is higher than the other. That's all it matters. Okay, but again, you take it step by step. You assign the current direction. From the current direction, you can assign polarity. From the polarity, you can write out the difference in the node voltages. So now, if I wish to apply KCL, I can apply KCL at node B. KCL at node B would give me current entering is I1, currents leaving are I2 and I3. Okay, I1 is entering, I2 and I3 are leaving. And then I use Ohm's law. Use Ohm's law to express each individual current in terms of the resistor voltage. So I1 becomes VR1 divided by R1. I2 becomes VR2 divided by R2. And then I3 becomes VR3 divided by R3. So far, so good. All right. Then one more step is expressing each resistor voltage in terms of the node voltage. So I can write VR1 is equal to VA minus VB divided by R1. Oh, not it's equals. VR2 is VB minus VC divided by R2. And then VR3 is VB minus VD divided by R3. Where VA, VB, VC, and VD are my unknown variables. Resistor values will be known. I will plug in the equations, and then I can reduce and get a set of linear equations. All right, questions? Any questions at all? Yes. It's just one of the equations. Again, if it's part of a larger circuit, we may have many different nodes in the circuit. And so it depends on how many. So that's going to be my next point. Basically, we are trying to find the unknown voltages, right? Unknown resistor voltages, actually. The components are the resistors. We wish to find the resistor voltages and the resistor currents. But we define node voltages and then we solve for the node voltages. Once we have the node voltages, we can find any resistor voltage we want. We already have VR1 as equal to VA minus VB. So once we have the values for VA and VB, we can find VR1. If we have VR1, we can find I1. Make sense to everyone? So the goal here is to minimize the work, right? When we first count the number of nodes in the circuit, let's say, for instance, we have 4 nodes, as we see here, A, B, C, D. We have to pick a reference node, right? So what value would that reference node have? 0. So it'd be 0 volts. We eliminated one unknown variable. If you have a voltage source in a circuit, as I stated last class in this slide, if you have a voltage source in a circuit, choose one end of the voltage source as your reference. So you have 0 volts at one end, and the other end of the source gives you one more value for one more node. So now you have eliminated 2 nodes, okay, from your unknown. So in this circuit, we have 1, 2, 3, 4 nodes. Out of 4 nodes, we choose A as the reference. So VA is 0, and B is connected to VS. So VB is equal to VS. So out of 4 nodes, we eliminated 2. So only 2 unknown variables. we only need to write two KCL equations to obtain two linear equations to obtain our answers. All right, questions? Shall we go to the example? All right, let's go. Oh, summary before that. Always forget the summary. Identify all the nodes, label all the nodes, and label all the node voltages. Plus label. Okay. And then, of course, you select a reference node. The reference node is automatically assigned a value of 0 volts. Then, this is important. You assume a branch current and you assume a direction for the branch currents. The branch currents are the ones that are flowing through the resistors. Students often forget to do this, and then they skip a step and their entire solution turns out to be incorrect. So this is kind of important. You assign branch currents and you note it in the circuit diagram. Then you apply KCL at each and every node. Once you apply KCL, you have your equation. You apply Ohm's law, express each current, each branch current in terms of the resistor voltage, and then each resistor voltage can be expressed as a difference of the node voltages. Okay, let's see how the summary would help us solve this example. How many nodes do we see in the circuit? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 nodes. I see some nods. I see some shakes. 5. Somebody says 5. I say 10. It's not a verbal quiz. You're not going to lose points. So please use your brains and tell me how many nodes we see in the circuit. To recap, a node is a connection between any two or more components. A wire is a node. It could be a small dot. It could be a small line. It could be a very long wire of 100 foot or hundreds of feet long. Transmission lines that go hundreds of miles long is still electrically the exact same node. So now how many do we see? She says 3, 6, half a dozen. The rest have no opinion. 3, 3, 6, 6. The rest get 0, they get 6 points. Then somebody will speak up. No, there are no points. It's a verbal quiz. 1, 2, 3. Again, concept. Again, I don't do this to embarrass students, okay? This is the point. It's a learning thing, right? So I want the students to take a crack at it first. If I give you the answers, then you are not learning. So I like to have students give me the answers. Okay, so again, the concept, this is how you should relate and try to identify nodes. Wire is a node. If you see two dots in a circuit and there is nothing except a wire between the two dots, that's a node. Okay, a dot does not mean, like a dot like this, does not mean they are two separate nodes. If it's simply a wire between the two nodes, if it's simply a line, that's the exact same node. That's how you would identify nodes. Okay, so it doesn't matter how many wires or connections you have, it's all exactly the same node. That's why I like this example a lot. Okay, so the first step was to identify all the nodes in the circuit and assign node voltages, right? And this example I really like because the answers in the end will turn out to be negative, depending on the reference node that I choose. So I'm going to choose C as my reference node. Oh, sorry, I haven't labeled it yet. I'll call this A, call this B, and I call this C. I will choose C as my reference. Therefore, VC is equal to 0 volts. There is no voltage source in the circuit. So but there is a current source, which is kind of an advantage because current source I can include in the KCL expression and I have a value for that current source automatically. Okay, I'm going to draw this large. Let's do this. One other thing, what else do you see? Look at the 4 resistors. Anything in series? Anything in parallel? Yes, I see some nods. Which one is in parallel? Or which one is in series? No? It's fine. You can speak up. It doesn't matter if it's incorrect or not. We're here to learn. What is connected between 2 nodes? The same 2 nodes. So R1, R2, and R3. Let's see. R1 and R4 at first glance might seem parallel, but R1 is connected between A and C, right? And then is anything else connected between A and C? Current source I1. So I1 is in parallel with R1. However, there is no other resistor connected between A and C. How about B and C? R4 and the current source I2. So they are in parallel too. They are in parallel and they are in parallel. And more importantly, when we look at the resistors R3 and R2, they are connected between A and B. And if both of their terminals are connected to the same nodes, then they are in parallel. So before you begin your analysis, you want to identify all the nodes that are in parallel and all the nodes that are in series. Especially for node voltage analysis, you want to identify the components that are in series, because if you have 2 resistors in series, there is a node between the 2 resistors. If you combine them together, you have now eliminated one unknown variable. Okay. The same concept would apply to mesh current when it's in parallel, but that's for later time. So we combine R2 and R3 in parallel. We will say R2 is in parallel with R3, and I'm going to call that as R23. And R23 is given by 2000 times 10,000 divided by 2000 plus 10,000. And that should give me a value of 1666.667 ohms. Those two are in parallel. I combine it. Now I'm ready to draw out my circuit diagram. And I'm going to draw this large, which is what I would expect of the students also. And there's a reason, because you have to note all quantities in there on the diagram itself. Then I'm going to draw. So this is going to be R23. This is R1. This is R2. And then I2 somewhere to the right. I'm going to ignore that ground. I don't really need that ground. Okay. This is A, this is B, and this is C at the bottom. I1 goes up. I1 is going up, going towards the right. So I'm going to choose a current for R23 also going from left to right. So I will choose IR23 is going from left to right. Then I would choose, let me mark it down here, IR1 the current flowing through resistor R1 as going from top to bottom, and current for R2 would be IR2 going from top to bottom. And I have I2 coming down. I2 has a value of 50 milliamps. This is 10 milliamps. Yes. Oh, yes. Sorry. R4. Thank you. R4. IR4. Okay. So my setup of the problem is almost there. What else is remaining for the setup? We identified and labeled all the nodes. We labeled the node voltages. I need to choose a reference node. And then if I choose C as my reference, I can write VC is equal to 0 volts. What else? What else is left? Any guesses? Any ideas? We marked, labeled the nodes, node voltages. We chose current directions. How about voltage polarities? So do not forget voltage polarities. This would be VR1. This is going to be VR4. And right at the top, I will mark out VR23. This will help you in writing out your equations correctly. So do not skip this step. Once you identify all the currents along with the current directions, do not skip over the voltage polarity. Okay. And now I'm ready to write my KCL expressions. So A, B, and C. C is 0 volts. I can write my KCL expression at any of these three nodes. But I just need two. I have two unknown variables, right? C is 0, A and B are unknowns. I can apply KCL at A, I can apply KCL at B, or I can apply KCL at C. The trick to choosing this, or not trick, the logic to choosing which node to apply is to look at the connections. How many connections do you have at a node? Those will be the number of terms you will have in your equation. So I have three connections at A and B, I will have three terms in my equation. I have four connections at node C, I will have four terms in my equation. And so I'll choose A and B. In this case, actually, it doesn't matter because two of the terms are constants, 10 milliamps and 50 milliamps. But in some other problems or in some other circuits, it might create a problem. And when I say problem, it might make it a little bit more complex. That's all. So I would apply KCL at node A. That would give me current I1 entering and IR1 leaving and IR23 also as leaving. Then you apply Ohm's law to this equation, and I can write I1 is VR1 or R1. IR23 is VR23 divided by R23. Then at this point, I will substitute the resistor voltages with the node voltages. And at the same time, I will also plug in all the known values that are given to me. The known values are the value of the current source. So I1 is 10 milliamps. So it's 0.01. VR1 I can express as VA minus VB. Oh, sorry, VA minus VC. R1 is 1000 ohms. VR23 is VA minus VB divided by 1666.667 At this point, I'm going to multiply this entire equation times 1,000. You can solve this or calculate this however you want from this point on. Okay, this is just math. As engineers, I would assume that everyone is capable of solving this. So use a calculator, use determinants, matrix, MATLAB, doesn't matter what tool you wish. Any tool you want, you choose that tool and you solve these equations. So we would reduce this. I'm going to do this manually. So 0.01 times 1,000 gives me 10 equals VC is 0. So this simply gives me VA plus 0.5999 VA minus VB. Rearrange the terms and I get 1.5999 VA plus, oh, sorry, not plus, minus 0.5999 VB equals 10. Made a hash of this. Oh, no, it worked out. I'm going to call this equation 1. AX plus or minus BY equals C, where X and Y are my unknown variables. In this case, VA and VB, the node voltages. Take 10 seconds. Let me know if you have any questions. Any questions at all? Yes. Because we chose our current direction as going from left to right. So I'm stating VR23 has a plus on the left and minus on the right. So then it would be VA minus VB. Let's see, did I do it correctly? Yeah. So IR1 is coming down, IR4 is coming down. So VR1 has plus a top minus down here. VR4 has plus up top minus down there. So IR1 would be VA minus VC. IR4 would be VB minus VC. And then for VR23, it would be VA minus VB. That'd be the answer. Yeah. So that's a good question. Again, when we write out the expression, you make an assumption at the top of the problem setup, right? So every sign, whether it's plus or minus in terms of the current and the node voltages, comes from the assumptions that you make at the beginning of your analysis. Once you make that assumption, you stick with that assumptions all the way through the end. Okay, even if your answer turns out to be negative, you do not change those assumptions. And I will explain when we try to calculate the resistor voltages. Again, remember, the end goal is to determine the resistor voltages and the resistor currents, right? So we will find that even if the answer is negative. Okay, so then I'm going to apply, let's go to the left. And I'm going to apply KCL at node B. I could apply it at C also. Doesn't really matter. Apply at any node, doesn't really matter. Let's see, 1044. Let's pick up the pace a little bit. At B, I have IR23 coming in. I have IR4 leaving. And I have I2, the current source, also leaving. Apply Ohm's law, and I obtain VR23 divided by R23 equals VR4 divided by R4 plus my current source, I2. Again, do not skip this step. Apply Ohm's law and write it out. Some students like to take a shortcut. They think they won't have enough time to solve. And so they take a shortcut and they skip over this step. I strongly recommend students not skip this step. Okay, write it out. Write out the Ohm's law. And then resistor voltages. This remains the same. That doesn't change because my current direction is still the same. I chose IR23 going towards the right. So it enters the left point, so the left point is higher. So VA minus VB divided by R23 equals VR4 is VB minus VC. Why is it doing this? Let's see. Okay, VB minus VC divided by R4. And then I2 is this is the current source. I'll do it in the next step. Now, actually, you know what? Let me go ahead and do it now. So R4, this is 0.05. R23 is 1666.667. R4 is 2000. So this time I will multiply the equation by 2000. That gives me 1.199 times VA minus VB equals VB plus 100. Rearrange the terms, and I would obtain 1.199 VA minus 2.1999 VB equals 100. And I will call this as equation 2. Two unknown variables, I only need 2 equations. I don't need a third. Solve 1 and 2 using any method you prefer. And you would obtain an answer for VA as promised, it is negative. Both of them. So does that mean your answers are incorrect? No. It simply indicates the level of the nodes. Okay, I'll wait for 10 seconds. You think on those equations while you're writing it out. Let me know if you have any questions. Any questions for anyone? Again, the important part is the problem setup. Once you have the circuit diagram correct, you make your assumptions, your current directions, voltage polarities. That's more than half the work is done, or at least half the work is done. Then you simply apply KCL and take it 3 steps. Apply KCL, write out the currents, then apply Ohm's law, and then apply node voltages. From that point on, once you plug in the values, it's just, I want to say, not quite middle school math, but at least high school math. And again, we have powerful tools nowadays, right? We have MATLAB solvers. You can simply plug the equations in MATLAB. It'll give you an answer. Plug it into a programmable calculator. That's why I always like to tell students, bring your calculators to every class. You can program these equations in that calculator, and you simply have your answers. Now, let's see what this means. C is my reference, both my voltages minus. So all it means is that both these voltages are below sea level. They're underwater. If I draw a 2-dimensional graph and I plot the points, let's say C is 0 volts. Where is A? I just told you they're underwater. So it's right here. It's 13 volts below C, right? And B is 52 volts below C. And this is the reason why it does not matter what you choose as your reference point. B is 52.857 volts. Let's say these 5 students choose C as their reference and the rest of the class chooses A as their reference. Some of your answers will match up, some of them won't. And when I say match up, I'm talking about numerical magnitude. So let's say the left side of the class chooses A as the reference point. So A would be here. Now A has a value of 0 volts, right? A is a reference value of 0 volts. The level of C will still be the same. But instead of down, you're now looking up. And C will have a value of 13.569 volts. So when I say the answers would be the same, is the magnitude is the same, but VC was 0 for these students here, and VC is 13.5 volts for the students on the left, as an example. V would be completely different. B would be equal to about 13.9. Actually, I will not put a minus in there because it's a graphical illustration. The minus is implied by the down arrow showing me that B is below. Okay, so it'll be 39 point. $39.398 volts. That would be the answer for VB. But the graph, when you plot it out, would be exactly the same. When you calculate your resistor values, they also will be exactly the same. Okay, even though your node voltages are different, your resistor voltage answers would be the same. And that's why it does not matter what node you choose as your reference node. Let's take a pause while you think over that, and I'm going to write out an example for the resistor voltage. Any questions? Any questions at all? So this is the assumption we made at the beginning of the problem. C is reference, right? So C is 0 volts. I obtain B as minus. So if I want to calculate resistor voltage VR4, the equation would still be VB minus VC. That does not change. When I say stick with the assumptions in the end of the problem, that means until you find all resistor voltages. Okay, that's the goal, right? Find all resistor voltages, find all resistor currents. So our current direction we chose was going from top to bottom, from B to C. So the equation still remains the same, VB minus VC. That does not change. That would simply mean VR4 is minus 52.857 volts. That's it. You do not have to indicate the new polarity saying that, okay, it's minus, so the polarity is flipped. You don't have to do anything. I will look at these values and I will look at the assumptions you made in the circuit diagram. If they match up, you will receive full credit. If they don't match up, then there will be deduction of points. Okay, you do not have to sit there and explain anything. Okay. All right, questions? Any questions? We still have 5 minutes. Do the steps make sense? Okay. So who wants to come up here and explain supernode? Sounds like something from a superhero movie or something, but it's not. Like voltage and current division, this is simply a shortcut. Okay. If we have one voltage source in a circuit, we can choose one end of the one source as a reference point, and we have an answer for the node at the other end, right? But what if you have more than one voltage source? If you have more than one voltage source, we cannot take, unless they are connected at one single node, we cannot take or eliminate that voltage source. So how do we write a KCL expression? We cannot write a KCL expression, right? For KCL expression, I can express each resistor voltage in terms of Ohm's law, using Ohm's law. But how can I do that for, let's say, my 50? If I choose V1 as my reference node, how can I write a expression for the current through 15 volts? We can't. If we cannot write an expression, what we can do is we eliminate it. So supernode is simply a shortcut. Simply a shortcut, what you're going to do is you draw a loop around that node, and all you're doing is you are basically shorting out that voltage source and treating this entire node as one single node. That's it. Supernode is just taking two nodes and combining them together. That is all you're doing. You're not doing anything else. So it sounds some fantastical concept, but again, as I said, it's like voltage and current division. It's simply a shortcut. All you're doing is you short out the voltage source, combine both nodes together to form one big node, and you write a KCL expression around that node. The logical explanation for this is very simple. You're applying KCL at both ends of that voltage source. Let me draw this out here. So if I have a voltage source like this, they have 2 minutes left. If you have to leave at 11, that's fine. I'll continue explaining this and I will record it. Okay, it's being recorded. So I will call this node up top as X. I will call the node below as Y. Okay. And I have so I'm only drawing out what is necessary. So I have let's see my notes. Okay, current directions. I'm going to write out this as IR1 coming from the top. I will write out this as IR3. This, the current flowing through the voltage source of 15 volts, I'm going to write as IS1. IR2 and IR, sorry, this is IR2, this is IR4. If A equals X and B equals X, is A equal to B? That's all we are doing. We are at KCL at X. We express the two currents in terms of IS1. We write KCL at Y. We express both currents in terms of IS1 again. So IS1 equals something. Second equation will be IS1 equals something else. We equate both of those together. We eliminate IS1. So you're just applying KCL at both ends. But supernode is simply you eliminate it. So you will skip all of those steps. That's all you're doing. So that's the concept. So KCL at X gives me IR1 plus IR3 equals IS1. And at the other end, I can write KCL at Y is equal to IS1 coming in, IR4 coming in, IR2 leaving. Therefore, IS1 equals IR2 minus IR4. I equate both of them together. I can conclude IR1 plus IR3 equals IR2 minus IR4. What supernode concept allows me to do is I can eliminate all of these steps. That's it. Basically, two KCL expressions saves me time. That's what it is, nothing else. You're simply shorting it out. So if I short that out, this is how it would look. I have the resistor here, I have the node here, another resistor here. This node is connected. So then I have current coming in, current coming in, current coming in, and this current leaving. 1, 2, 3. Let's see, wait. Yeah, IR1, IR3, and IR4 coming in, and then IR2 is leaving, which is the exact same expression we have here. IR1, IR3 plus IR4 equals IR2. Okay, that's all it is. Supernode is just a shortcut. Okay, we'll end class here today. If you have any questions, I have a few more minutes before my next class. I will be in my office between 4 and 5 p.m. Prior to 4 o'clock, I will not be. If you have any questions, send me an email. I'd be more than happy to answer. Otherwise, I will see you all on Monday.